Okay, if you have a number like this, then the best way to figure out how to add these numbers is you can do it in your calculator, but your calculator is not very helpful in terms of rounding off. Okay, this number, 5.6 times 10 to the 2 is really this number. Okay, 5.6 times 10 to the 2 is 560. Removing the decimal place, two decimal place over 560. You notice it's positive 2, that number is bigger than 1. This number, 2.3 times 10 to the third, that number is 2300. Again, the exponent is positive, that number better be greater than 1. Both has 2 significant figures. This one is to the 10th place. That's the degree of precision. This one is to the 100th place. That's the degree of precision. Okay, because it comes from this value right here. This 3 is to the 100th place. It's 3 places to the left of the decimal. So when you add this, and you can do this in your head, it comes out to 2860. But then you have to use the rules of significant figures. You can't just keep 2,860. That would be wrong. And you can't write 286 because 286 is not 2,860. Okay, you could write it as 286 times 10 to the first. You can write it that way. Or you can write it as 28.6 times 10 to the second. You can write it that way. But is it really still the correct answer? And the answer is no. Then that's because the 6 here should not be there because it's not significant. So think about that a moment. I've got a number right here, 2,860, based on adding 560 and 2,300. And yet I'm telling you, writing 2,860 is incorrect. Why is it incorrect? And the reason why it's incorrect is because you're reporting a number that has higher uncertainty. Uncertainty has to do with the error in that number than the data that you collected. Think about that a moment. Let me say that again because I want to make sure it's clear. When you add 560 to 2,300 and you get 2,860, and you keep that number, you're writing a number that has more error than the data that you are using. So let me elaborate on that. Okay, first of all, you've got to understand the difference between precision, least precise, versus significant figures. If I measure, say, the length of this paper, okay, and I tell you, oh, it's about maybe a foot, 12 inches, then you're going to have some sort of approximation. If I tell you that this is 11.78 inches, then that's more precise because I'm telling you a measurement to the 100th of an inch, okay, plus or minus 0.01, 11.86 inches to the 100th of place. So that's a finer measurement than if I told you it was a foot, because a foot is plus or minus an inch or two. Okay, so that's what I mean by least precise versus most precise. Least precise is an approximation that tells you that the size, the incremental size is bigger than more precise. More precise will be finer readings. Least precise will be bigger readings in terms of the increment. Okay, so if we have a number like 123 versus 1.2, and I ask you, which of these have the fewest significant figures? Then hopefully you guys say the fewest significant figures is 1.2 because it only has 2 significant figures. Okay? It only has 2 significant figures. Oops. So that would be 1.2. But which one is least precise? Which one is going to have the more coarse reading? Well, this is to the first, this is to the 10th. So the least precise is 123 because that's plus or minus 1 versus 1.2, which is plus or minus 0.01. Sorry about that. Plus or minus 0.1. The rightmost digits is your uncertainty. And the rightmost digit here is to the 10th of a place. Here, your rightmost digit is to the first place. So you can see that the 0.1 is smaller than 1. So it's more precise. Least precise is 123. Let's take a look at 1.23 versus 1.200. Significant figures. 1.23 only has three significant figures. 1.200 has 4 significant figures. Which one is the least precise? Well, 1.23 is plus or minus 0.01. 1.200 is plus or minus 0.001. That's more fine than the other. So the least precise is 1.23 between the two numbers. Okay, let's take a look at 0.123 versus 0.00012. Fewest significant figures would be this. It only has 2 significant figures. The other one has 3 significant figures. Which one is the least precise? This one reads it all the way to the 5th place. That's 10th of 1,000th. This one reads it to the 3rd place. That's 1,000th. So the least precise is 0.123. It's going to have a bigger incremental reading than the other one, which is more fine. Finally, the last one, 30 versus 36. 30 only has 1 significant figure. 3600 has 2 significant figures, the 3 and the 6. Which one is the least precise? 30 is plus or minus 10. 3600 is plus or minus 100. So the least precise is 3600. Now, why did we do all of that exercise? Well, we did all that exercise because when you add numbers together, you're going to have to round off based on your least precise value when you add it up, only when you add or subtract. Take this example. I go to someone's donating money. You can see right here that this is $2.52. Easily read. You can read it to the penny. This right here is $3.26. Again, you can read it to the penny. But this right here, I can't really read all those pennies. Okay, I can probably approximate it that maybe this happens to be like 20 cents or something, but it's going to be plus or minus 5. That would be like 70 cents plus or minus 0.05 cents because there's a degree of uncertainty. So again, your answer can only have a degree of uncertainty, a degree of error based on the data which has the greatest error. Let's take a look at this example right here. See this number right here? It has 2 significant figures, the 5 and the 6. This number has 2 significant figures, but one is to the 10th place, the other is to the 100th place. This has the biggest error. Sorry, not that. This right here has the biggest error. Because that's plus or minus 100. Your 3 right there is the 2 and the 3 are significant, but the 3 is your rightmost digit that is significant, so it's plus or minus 100. So your answer here, 2860, has to have an error of plus or minus 100 as well, because your data, the biggest uncertainty in your data, the least precise is the 2300 that you're putting. So you're going to write an answer that is plus or minus 100. So the correct answer is 2.9, because we're rounding off the 8 to a 9 because 60 is above the halfway mark, times 10 to the third. That would be the correct answer when you add and subtract, because you're rounding off based on the least precise value. Addition and subtraction is much more complicated than multiplication and division, because you have to look at all the data and you have to figure out which one of those has the biggest error. It's the least precise. Here, let me move on because I want to do this right here. Say we have this. Do this exercise real quick. 1062 times 10 to the second. That number is 1062. Okay. 10.62 times 10 to the second is 1062, and that's plus or minus 1. This number 1.223 times 10 to the fourth, that would be 12300. But that's plus or minus to the 100, because the 1, the 2, and the 3 are significant. The 3 is the rightmost digit, and when you convert that exponential notation to a real number, it comes out to 12,300. So when you add this, 2, 6, 3, 3, 1, 13,362, again, 12,300 and 1062, 26331, okay, 13362. Your error is going to be based on this value right here. So that's how you're going to have to round it off. You're going to put in your data sheet 13362, but then you're going to write, based on rounding off, 134 times 10 to the fourth. Or you could also write this, 13400. Both have 3 significant figures. Both is rounded off to the 100 place, and both keeps the same magnitude of the number. Both says it's about 13,400. Okay. So again, addition and subtraction, you're looking at the data that you're using, looking for the least precise, the one that has the biggest error, and you're rounding off based on that. Let's try another one. Let's try this one right here. Okay, because the rest of these are multiplication and division. So this one again is 1062. And in this particular case, I'm subtracting 1.63 times 10 to the third. 1.63 times 10 to the third is 1630. Okay, 1.63 times 10 to the third is 1.630. And so if I do this, and I have my calculator here, because I'm going to get a negative number, because 1.63 times 10 to the third is bigger than 1062. So I'm going to put 1062, 1630, and I'm going to subtract that, and I get negative 568. Okay, that's my answer. But let's take a look at the data again. This is plus or minus 1. Why is it plus or minus 1? Because the 1, the 0, the 6, and the 2 are significant, and the 2 is in the first place. This is plus or minus 10. Why? Because only the 1, the 6, and the 3 are significant, and the 3, the rightmost digit, is into the 10th place. So that's why it's plus or minus 10. So your answer has to reflect that. It has to be plus or minus 10. So in order to make this plus or minus 10, it'd be minus 570. You got to round the 68 to a 70. Okay, minus 570 is your answer for this particular case. Actually, yeah, that would be correct. 570, and you want to put a dot there to show that there are 3 significant figures in this particular answer, but it's to the, no, you don't put a dot. I apologize for that. You don't put a dot there because that's 0. If you put a dot there, then that 0 becomes significant. Okay. Let me fix that real quick. Oops. And let me try and explain that again. Because I hope I didn't confuse you guys. Okay. That right there would be the correct answer, 570. The better way to do this, okay, is 5.7 times 10 to the, in this particular case, 2. Now, why am I rounding it off to 570? Here I've got 4 significant figures. Here I have 3 significant figures. And yet, when I get my final answer, it's 2 significant figures. That really could be confusing. Here's a little hint that I want to share with you guys. Whenever you add and subtract, okay, add and subtract, you can gain significant figures or you can lose significant figures. But your answer is based on precision, okay? Precision, rounding off to the biggest error. So adding numbers or losing numbers is not important in addition and subtraction. Here we're losing significant figures. We go from 4 significant figures and 3 significant figures down to 2 in our final answer. But the degree of precision is still the same. The degree of precision for 1,630 is plus or minus 10. The degree of precision for 570 is plus or minus 10. Because the 7 is in the 10th place. In addition and subtraction, you can lose or gain significant figures, but your precision has to be consistent. If your biggest error is plus or minus 100, your answer better be plus or minus 100. If your biggest uncertainty in your data is plus or minus 10, your answer has to reflect plus or minus 10. You can gain numbers, you can lose numbers, but that precision has to be the same. So this answer, 570, negative 570, or negative 5.7 times 10 to the second, is going to tell you that the error is plus or minus 10. This right here would be translated as this, and that's plus or minus 10. I know that's why it's confusing on this first activity, because you have all these weird rules. But when you practice it, it becomes easier. Okay? So that's addition and subtraction. Addition and subtraction. When you come up with multiplication and division is super easy. Why? Because all you've got to do is look at the significant figures and round off your final answer based on that. Okay, this has 4 significant figures. This has 2 significant figures. My answer has to have 2 significant figures. I don't even have to do the calculation. I know my answer has to have 2 significant figures because it's based on the fewest significant figures. This has 3 significant figures. This has 3 significant figures. My answer better have 3 significant figures. It's not based on precision, okay? The least precise or the most precise. It's based on significant figures. This has 2 significant figures. This has 4 significant figures. My answer better have 2 significant figures. Addition, multiplication, division is so much easier than addition and subtraction. All I've got to do is look at the answer. Look at the data and round it off based on the fewest significant figures. So I'll do this last one right here. This last one, I'll do it for you. I'm going to put in my calculator. And again, it's best when you do it in your calculator because then you can see this. Let's see if I have a calculator in my computer. That way you can see how I do it. So I'm just going to pull out the calculator. Okay. And get that. Here it is. And if you have an Apple, you can actually make this a scientific calculator by going up here, and you can do science or basic. I'm not going to do program. So I'm just going to do science. And in this particular case, I'm going to put 8.6 to the EE second. Okay, so that's my number down here, times 2.3 to the third equals. So that's the number I would put down in the first parentheses, 1,978,000. That would be the answer. Now, notice I said that this answer should be rounded off to two significant figures. Well, two significant figures would be this right here. It would be let me write the entire answer here first. So two significant figures would just be that, but the 9 is, to the right of the 9, there's a 78. So it has to be bumped up. So that means that this number really is, this needs to be bumped up to, in this particular case, 2.0 times 10 to the 6. 36. So that would be your answer. 2.0 times 10 to the 6, because you got to round off the 9 up because of the 78, and you're keeping two significant figures. 2.0 has two significant figures. Or, yeah, that's the way you would write it. If you wrote it this way, that would be wrong. Why? Because that number only contains one significant figure. There's no decimal point here. So that would be incorrect. If you wrote it this way, that too would be wrong. Why? Because that number has 7 significant figures because of the decimal. The only way you're going to preserve two significant figures and still retain that number is to write it in scientific notation. 2.0 times 10 to the 6. This is the only way in which you can write that number with two significant figures and still retain the magnitude of that number. You're not going to write 2.0 because 2.0 is not 2 million, okay? You're not going to write 2.0 because 2.0 is not 2 million. And you're not going to write 2 million with a decimal point at the end because that would be 7 significant figures. And you're not going to write 2 million with no decimal because that would be 1 significant figures. You can see the dilemma. That's why we use scientific notation. But nevertheless, addition and subtraction is much more complicated when you do the math than multiplication and division. In multiplication and division, you can just look at the fewest significant figures, and that's how you're going to round off. That's how you're going to round off. So these are just examples of that in the PowerPoint. What happens when you have a mix? Okay, when you have a mix, then you have to apply. You need to look at this right here. You need to apply the rules of addition and subtraction within the parentheses, round off to the number of significant figures. So let's take a look at this. This right here, let me just, this is your final answer. And how did I get that? Well, I took this right here. Okay, 33.792 and 31.426. So let's do that in the calculator. 33.792 minus 31.426. This has to be kept to the thousandth of a place because both digits are 3 digits past the decimal. So you have to keep it to the thousandth of a place. But notice you lose significant figures. You go from 33.792 and 31.426 to 2.366. That's only 4 significant figures. So this bottom one is now 2.366. You have to keep it to the thousandth of a place because that's the rules of addition and subtraction. Let's do the top now. The top is 48.35. Oops. Let's clear that. 48.35. And I'm subtracting 35. Oops. Sorry about that. I forgot to say 48.35. And I'm subtracting 35.18. Again, both of these are to the 100th of a place. So my final answer should be to the 100th of a place as well, 13.17. And I'm multiplying this by 0.12. So both of these numbers right here are based on the operation of addition and subtraction. Addition and subtraction, you use the least precise. The least precise for both of these is to the 1,000th of a place for the bottom, to the 100th of a place for the top. So I have that. Now I'm multiplying it by 0.12, and now this is a multiplication division problem. The fewest significant figures is 0.12. It's only got 2. So my final answer is going to be rounded off to 2 significant figures. So I'm going to take this number, multiply it by 0.12, and then I'm going to take that answer and divide by 2.366, and I get that number. Okay, it's a number that has a lot of digits, but I know that my final answer, because I'm now doing multiplication division, should have 2 significant figures. So my final answer here would be 0.667. So for mixed operation, carry out the addition and subtraction, especially the ones that are in parentheses first. Then you can do the multiplication and division. It's always based on the parentheses. That's your order of operation. And then you can work out the problem. Here, I'm multiplying. Let me get this out of the way real quick. Here, I'm taking 3 significant figures and multiplying it by 6 significant figures. So my answer should be 3 significant figures. And then in this parentheses, I'm taking 4 significant figures and multiplying it by 6 significant figures. My answer should be 4 significant figures. But then I'm adding it. Notice I'm adding it. I'm adding 0.446 to 0.01760. This one has the biggest error. This has a plus or minus to the 1,000th. This has an error to the 10th of thousands. So I have to round off my final answer based on this right here. It should be based on to the 1,000th of a place. So when I add 0.446 to 0.01760, let me show you that in the calculator just so that you can see that. So I'm going to clear this. I'm going to take 0.446 and I'm going to add that to 0.01760. Okay, I get a number like that. But I know that my least precise is 446. I need to round it off to 3 digits past the decimal. So my final answer, I don't know why I did that. This 0.446, this answer is incorrect, by the way, 0.422. I don't know why that's the case. I know that's not correct. I need to correct that real quick because this right here is not correct. This should be 0.446 plus 0.01760 should be 0.4636, and then I need to round off to the 1,000th of place, so it's 0.464. Okay, that would be my final answer for this particular problem. I don't know why I put that in there. Okay,
are these slides
available? Yes, they are. Okay, I'll put them up in Canvas. So again, when you have mixed operation, always go within the parentheses first, and then use the rules that we talked about. The rules that we just talked about, addition, subtraction, multiplication, division, that's probably the hardest of this activity. Okay, that's the hardest of this activity. So what I'm going to do now, because we're pretty much done with this part, let me do this real quick.
Excuse
pretty
me.
much done with this part, is we're going to...
Correct. It's 0.622. It's correct on the slide.
Okay, let me take a look. 0.622 when I take 0.446 and I add 0.01760.
Yeah, I did the same thing. Yeah, it's 0.622.
That's weird. Let me try that. Let's do this together again, okay? Because I can tell you right now that this number is less than 0.2. So that's the reason why. If you multiply it, maybe, but I don't think that's the case. Let me try that again. 0.446 plus 0.0176, okay, equals, that's what I got. You might want to...
I forgot the zero. Yeah, 0.017.
Yeah, okay, 0.0176. If the decimal point was here, then that would be incorrect. Okay, yeah, like I said, let's try this. 0.9258 times 0.190100 equals... Oh, yes, you're exactly right. This number is incorrect. I apologize for that. It should be, oh man, thanks for finding out my mistake. This number should be 0.1760. If you take 0.9258, you're exactly right, and multiply it by 0.190100. Multiply those two numbers, you get 0.17599. Four significant figures would put it at 0.1760. You're exactly right. The answer is 0.622. You gotta excuse me, okay? I might as well admit this now. I'm slightly dyslexic. Whenever I see zeros and dots, sometimes I interpose them. And so the correct answer would be 0.622, because this answer right here is 0.1760. I apologize for that, okay? So let me just do this real quick. I'm going to put you in a breakout room for about 15 minutes, and you guys are going to go over this activity and look at them and work on it for a while, help each other out, this right here. And then when we get back, you guys are just going to shout out some answers to me, okay? And just randomly, and then we'll finish the last part on dimensional analysis. So here again, make sure that you guys know how to round off. Here, make sure you know how to do significant figures. Here, make sure you know how to express these numbers in scientific notation. Here, this is probably the hardest, okay? This is where you probably want to spend your time with your group. Maybe some of you will do some of these and then double check your work. Okay, you don't need to complete it all, but I want you guys to work in your group. I'm gonna send you out to a breakout. There's probably about 3 of you in a group, and then work on some of these and compare answers. It's okay to compare because I said it's okay, okay? Then when you have your answers, you can see whether or not you're doing it correctly or not. If you have questions, you can ask your classmate, or you can ask me for clarification when we get back. As soon as we get back and I have all of you guys on the same